I'm going to be discussing the problem combination sum. The problem statement says given an array of distinct integers candidates and a target integer target, return a list of all unique combinations of candidates where the chosen numbers sum to target, and you may return the combinations in any order. The same number may be chosen from candidates an unlimited number of times. The two combinations are unique if the frequency of at least one of the chosen numbers is different. The test cases are generated such that the number of unique combinations that sum up to target is less than 150 combinations for the given input. The problem statement says that the difficult part about the problem is trying to figure out how to eliminate duplicate combinations. We need to try a decision tree that gets the results that we want but does not have the duplicates. The problem statement says that we need to find all the possible combinations from a candidate that sums up to the target. The next is we cannot use a particular number more than total number of elements present in the array. We need to scrap any combination where the number result becomes greater than the target. When we move on to the next element in the list, we cannot move backwards because we have visited all the elements when the counter was pointing at the previous element. The time complexity of this solution is big O of 2t. The solution code uses the DFS plus backtracking to explore every possible combinations that sum up to the target. First, candidates.sort function ensures the numbers are processed in increasing order, so we can break early when a number exceeds the remaining target. We maintain a global result list and define a recursive function comb curr, start, target, where cur represents the current combination. Start ensures we don't go backwards in the array, preventing duplicates, and target tracks the remaining sum. If target is equal to 0, we found a valid combination and embed it to the result. Otherwise, we iterate from start to the end, and for each candidate less than or equal to target, we continue exploring by adding the candidate to the current list and recursively calling the function with the same index I, because repetition is allowed, and the reduced target minus candidates of I. If a candidate is larger than the remaining target, we break because sorted order guarantees no later number will fit. The second approach is dynamic programming solution. The solution initializes results as an array where each index I stores all the unique combinations that form the sum I, beginning with base case result 0 is equal to empty array, meaning there is one way to make sum 0, choose nothing. For each candidate number canned, the code loops forward from end to target, from CA and D to target, and for every sum I, it looks at all combinations that can form I minus canned, stored in result of I minus canned, and extends each of them by appending canned. These new expanded combinations are pushed into result of I, meaning we have now discovered all ways to form sum of I using the candidate. The forward loop ensures each candidate can be reused unlimited times, unbounced knapsack behavior, and also guarantees no duplicate combinations with different orderings. When all candidates have been processed, the result of target contains every valid combination that adds up exactly to the target. The time complexity of this approach is big O of target, space complexity is also big O of target. So then the patterns which are observed while solving the problem are first is DP state array, second is bottom up built up, third is unbounced knapsack forward loop, fourth is arrays storing lists of combinations, fifth is loop order to avoid duplicates, sixth is state transitions using previous states, and then 7 is using arrays for combinatorial DP.